Morning, guys. So yesterday we had a look at vector addition. Essentially, we remember vectors are different from scalars. They don't just have magnitude, they actually imply a direction. We started seeing two-dimensional problems in yesterday's lesson where the horizontals are completely separate from the verticals. So as I walk east and west, it's completely unrelated to whether I go north or south. We're going to be utilizing that fact in today's lesson, bringing back some of those kinematic equations from earlier as well, in a section we call projectile motion. Usually we will do basic one-dimensional problems in Physics 11. We start getting more two-dimensional stuff sort of towards the end of Physics 11, starting Physics 12. I'm just going to give you an example of a three-dimensional problem. It's just the same step, but you have to do it one more time. So just going to do this just as an example. We'll see if we can sort of work our way through this problem here. And then today, like I mentioned, we're going to go through projectile motion and study two-dimensional problems in a little more detail. So just as a quick warm-up here, I'm interested in adding a couple of vectors here. So let's start off with a question here. A treasure is buried 10 meters north, 20 meters east, and 30 meters below ground. So I'm keeping the numbers fairly simple. So we have those sort of three directions there. The question here is, can you calculate the displacement? Very rarely do we do three-dimensional problems, but like I mentioned, you're just going to see, oh, it's basically what we do with two dimensions, but we have to do it one more time. So what I'm going to do here is I'm going to start off, we actually need two pictures this time. We'll start off with the first two instructions, which is sort of like a top view problem. I'm starting off somewhere, right? I have some coordinate here. They're telling me the instructions are the treasure is buried 10 meters north of me and 20 meters east. So 10 is smaller than 20. So the first arrow here, I'm going to label this 10 meters north. That one there, it's sort of, I need to head north first. And then I need to turn the corner here. I need to go farther away 20 meters in the eastward direction. You'll notice here, again, vectors have to be added head to tail. So the sort of the point of the arrow has to hit the back end of the other arrow. And you'll also notice that for vectors here, it doesn't matter the order that you add them in. So even though I did the north first and the east, had I done east first and then I done north here, I would have gotten to the same location in space. But anyway, so we have that direction there. So if that were a two-dimensional problem here, we would be interested in, well, what's the displacement here, right? How far northeast from where I'm standing? Let's find this angle. This time it's a little bit easier than the one before because each of these directions are pure north and pure east. None of these are diagonals. None of these do you need to actually break up components. So we just use Pythagoras right away. And then what it knows is when I walk there, that's only on ground level. Now if I switch over to sort of a side view picture, so looking from the side here, I see the person standing there here. I'm going to get him. I know he didn't actually walk this diagonal, but he is this diagonal D away from the treasure. That's already in the northeast direction. And you notice that this treasure is actually buried some 30 meters below ground, so downwards. So this is going to be 30 meters. This is going to be below. And what we eventually want, again, is from me standing on ground level, not only northeast towards the treasure point here on ground level, I want to actually point sort of a diagonal here from me ground level, also pointing downwards. Let's just call that a different one. Let's call it C. And I want to know this angle here just to indicate that this angle is different from the one before. Usually we use a different letter here, maybe phi. So theta was the first angle, that was the how much northeast, and this angle here, phi, actually gives me how many degrees below ground. So definitely a three-dimensional problem here, but you're going to see it's essentially what we do in two dimensions, and we do it twice. So we'll start off here with an easy question. So I know I had to walk 10 meters north and then 20 meters east. I know because I changed direction, my overall displacement, how far I am pushed from my starting point, from blindfold on to blindfold off, is not going to be 30 meters, right? It's going to be less. What we're going to do is we're just going to do Pythagoras here. The d is the hypotenuse side, so I could say d squared is equal to a squared plus b squared, right? And usually what we do is we actually already have solved it. D is the square root of a squared plus b squared. And in this case here we can say d is root 10 squared plus 20 squared. That's how you actually put the two directions back together, right? That's how right triangles actually really help us out here. I do that math there and I get here some 22.4 meters. Now again, because vectors need a direction, I could say, yeah, it's in the northeast direction, but again, we talked about yesterday, it gives you more information if I actually tell you the number of degrees as well. For the degrees, if you remember the formula itself, we know the opposite and the adjacent. We actually now know the hypotenuse as well, but just in case I got the hypotenuse wrong, I don't want that knocking off my next problem. So I'm going to use opposite over adjacent here. Tan theta is opposite over adjacent. And again, I'm just going to manipulate that right away. Theta is the inverse tan of opposite over adjacent. And I'm just going to plug it in over here. The inverse tan. For the angle that I drew, the opposite would be 20. That's the side I'm looking at. And the adjacent side is the 10. So I'm going to go 20 divided by 10. It's just a ratio. Make sure you're in degree mode. Inverse tan of 20 over 10 gives me here 63 degrees. Instead of just saying northeast, we start from the pure direction. So this line here is aiming pure north. And I'm aiming 63 degrees east from north. So therefore, I'm going to write this down here, east of north. Now remember I was saying here, well, vectors, the order doesn't matter. I could have gone east first and then I could have gone north afterwards. That actually would have sketched for you the other triangle. You may have found this angle instead, and we talked about here the angles are complementary. They always add up to 90 degrees. So even though I might call that angle north of east, that would be some maybe 27 degrees north of east. So if you're having trouble like matching up, how come the multiple choice answers aren't exactly what I got? Maybe it's the complementary angle. Maybe I drew the other triangle, and you can just simply go 90 minus 63 degrees. Make that little note here. This one could also be written 27 degrees north of east. So that deals with the two-dimensional problem. That's fine. And now if we switch over to the side view, we now know, all right, so from where I'm standing, if I go in this diagonal direction, this D here is actually 22.4. And now what I'm adding to this here is I'm going to be 22.4 on ground level. I'm going to dig 30 meters below ground. What is the sort of the diagonal again? Sort of from me on ground level here, going the diagonal northeast, but also down into the ground. I label that C. Again, just Pythagoras again. So you see, we did Pythagoras once just to get the 2-dimension. We're going to do it once more to get the 3rd dimension here. 22.4 squared plus 30 squared. So give or take a little bit of rounding here. 22.4 squared plus 30 squared with the square root. It tells me in total, from my starting point here on ground level, after you go the northeast diagonal and you also dig downwards 30 meters, the distance you are from the actual treasure that's below ground at this northeast direction is actually 37.4. This angle here, phi, this phi here is no longer the theta. It's not just the angle that it makes to the ground. This angle is somehow, it's below the flat plane. We're going to use our inverse tan again. Inverse tan is opposite over adjacent. In this case here, my opposite is 30 divided by 22.4. And that gives you here inverse tan 30 over 22.4, and we get 53 degrees. In this case here, while we're tempted to say, oh yeah, we're from the pure east direction, and then we're going to point south from there, be careful that this is actually a side view problem. A side view problem here has the conventions. This is just sort of right, this is up, right? We're talking up, down, left, right. We're not talking northeast, southwest anymore. So in this case here, you can say, well, if we call like just sort of the left and right here, if we call it the horizontal, we can call this angle here, let's say 53 degrees, below the horizontal, right? Because it's a side view, right? Imagine you're watching this on a projector or a TV screen here. When I aim down, it actually is lower, it's beneath the ground, so below the horizontal, right? So like I mentioned, I'm not going to be testing you on 3-dimensional problems. However, it's just what we did in 2D, but you have to do it one more time. Again, it reiterates this idea here. The dimensions here, they don't affect each other. You can do whatever you want on ground level. It doesn't affect the fact that this one here is 30 meters below ground. If this is 30 meters below ground in the side view picture here, it doesn't affect what the northeast southwest is. And we're going to carry that idea into the next couple classes. So let's start off into a newer section here. In general, we're going to call this next section here projectile motion. Projectile is something that is thrown, so we're going to be talking about, in today's lesson we'll call it like a meatball style question, but later on we're going to do like a football, right? I launch a football at an angle, I fire cannonballs off cliffs, okay? I'm interested in studying the projectile's motion, the projectile's path through the air. So I'm going to just start off here with just a thought experiment here. Imagine for a second here, I have 2 equal tennis balls, so I have one tennis ball, I have another tennis ball. And my experiment is actually quite simple. For the first tennis ball, all I'm going to do is I'm going to drop it. So both of them currently are at rest. Both of them have an initial velocity of 0. For the first tennis ball here, if I drop it, you'll know, well, gravity is an acceleration. We've been saying acceleration is a negative 9.8 meter per second squared. Throughout this chapter, we've been using negative just to imply direction, so that's downwards. There was a question earlier, we had defined that back as positive. It's fine, just make sure you're consistent. The tennis ball here that I drop, quite simply here, after the first second it starts dropping, after the next second it starts dropping a little bit faster, and eventually it's going to hit the ground below. Right? So that's just the tennis ball. Remember when we start talking about, for kinematics here, the final velocity is immediately before hitting. It's not upon colliding and now it's bouncing back and now it's losing its energy. It's not that. It's just from the start to immediately before hitting. So it's going to fall through a distance h. Well, we're going to compare in this experiment here. For the other tennis ball here, I'm actually going to launch it at a horizontal velocity, at a speed that's sort of going to the side. So naturally here you would sort of imply to me, well, this one here will eventually actually sort of curve and go downwards here. That one actually does make a really nice parabolic shape. It is definitely true that this one here actually will travel through more ground, right? If this one here I just fall downwards versus I follow down the curve, I actually travel more distance. What if I ask you the question here, which of these tennis balls, assuming that they're starting at the same height, which of these tennis balls here hits the ground first? Intuitively, we might actually guess, well, because this curve here is actually traveling more distance, of course this one will actually hit later. What we actually find is a little bit surprising. While you do launch it vertically, let's say t equals 0, I drop both objects, I push that object off. In fact, in 1 second, the height of that object is exactly the same as it was earlier. Maybe 2 seconds, it's at the same sort of height. And in fact, both objects actually collide at the same time. And then we say, well, how could this be? Right? This one here is actually traveling in 2 dimensions. Because, you can actually do this experiment for yourself, try it at home. Because horizontal and vertical are completely independent. We can break this projectile motion. We can break motion into x and y. And when we study the x, it's as if the y isn't happening. When we study the y, it's as if x isn't happening. So we actually get a good glimpse of this one here. This is going to be called the meatball question, where we're going to start out from a surface and we're going to push you sort of vertically off here, or just launch it horizontally here. In the horizontal, I can think about this curve here. It's sort of like horizontally, this object here starts here, later on it's a little bit pushed over, later on it's a little bit pushed over here. Horizontally, that's all the object is doing. It doesn't actually know it's falling. What about the vertical? For the vertical, it's like we start out from this height here, a little bit later we're actually falling downwards, a little bit later we're falling downwards. It's as if the vertical has no clue that we're actually being launched at a horizontal, and just like our north and south doesn't actually affect east and west, we can study these two parts of motion completely separately. So while it is still true, yes, because this motion here is 2-dimensional, I do actually travel through more distance here, but because the y here doesn't really care, I actually have an x velocity here, it's actually going to hit at the same time. So again, try it out for yourself here. Objects hit at the same time. Just sort of supporting the fact that, okay, it doesn't matter that this is actually going to be traveling through this sort of curve-like shape here. In the vertical, it's as if I drop the tennis ball. What I care is just, we launch it, we drop it from the same height, and we sort of let gravity pull it downwards. It's going to end up colliding and hitting the ground at exactly the same time. So, in today's question here, we're just going to start off analyzing these 2-dimensional problems. Through the next 2 lessons, we're going to continue this. For some reason, they call these ones here meatball questions. I have seen some worksheets actually say, imagine you had some spaghetti meatballs and then, there's a loose meatball and it's starting to roll off the table. It could be a meatball for that reason. Another sort of way of talking about meatball question, usually we talk about a meatball question as a car driving off cliffs. And then it's sort of like, you have to be meatball. You have to be like really not paying attention if you end up driving off a cliff. So for either of those reasons here, we call this a meatball style question. Let's just start off with a cliff here, just a standard meatball question. We're going to have our car. Again, the driver isn't paying attention. The velocity here, let's say currently is 50 kilometers per hour. And I'm going to point out to you here that this 50 kilometers per hour is just straight, right? Because the cliff here is perfectly flat here. This 50 kilometers per hour is perfectly horizontal. What it doesn't know is the instant that it actually leaves the ground, it's going to start falling. But because it had some horizontal velocity, like we saw for this second tennis ball, it's going to end up falling down this sort of parabolic shape. I'm interested in studying, depending on how high this cliff is, let's make it like a 100-meter tall cliff here. I'm interested in how far it's going to land. We're going to call that distance actually the range, right? So how far from the base of the cliff does it land? Usually in math class, range is sort of the y-axis, but in this case here, the range is how much ground is covered. I'll split this up into two parts. Question here. First A, find the time to reach the bottom. Right, so I need to fall through a distance of 100 meters. So how long does it take? And then B, like I mentioned, calculate the range. Calculate the distance from the base of the cliff. Right, so you can imagine here, well, I'm going at 50, right? If I were going faster than 50, I would end up going farther than that. If I was going slower than 50, I'd go a little bit less. But because I'm going exactly 50, where should I be from the base of the cliff here? How far should I be in front? How far should I put a target so that I would actually end up hitting this target here? And what I want to analyze for you here is we're going to study the x's as if it was completely irrelevant from the y's. So in the x direction, it's fairly boring. In the x direction here, your wheels are sort of spinning away here. They're trying to give you a constant 50 kilometers per hour. The second that your car leaves the cliff, this is when I'm going to start my clock. This is when things start getting interesting. This is when things start actually happening. Well, in the horizontal, why I say it's boring is, well, horizontally, I'm starting here. I was at 50 when I left it here. We're going to always assume in the horizontal, there's actually no air resistance. So what's going to happen is in a second later, I'm going to still be traveling 50. A second later, I'm still going to be traveling 50. A second later, I'm going to still be traveling 50 here. The x has no idea that we're going to be colliding, right? The x is just going to continue onwards at 50. What about in the y direction? We're sort of breaking up this parabola-like motion, studying into the two dimensions here. For the second dimension here, this part's a little more interesting. Well, the car starts out from the top of the cliff. We're 100 meters from the ground. Because we're now in free fall here. A second later here, we're going to start speeding downwards. There is an acceleration due to gravity, so we're going to fall faster and faster with each second, and eventually I'm going to hit the ground below. This is the y. And what I'm trying to show you here is, even though this dimension I can see is two dimensions, we can actually study. Let's just do the x's separately, and let's just do the y separately here. So normally I just tell people just set up two big columns in your notebook here. Let's do one column for the x, let's do one column for the y. And let's make a list of all the variables as we know them. Those kinematic formulas that are going to come back again in this lesson here. The kinematic equations work just for one dimension at a time. The biggest problem I see people do in this section is they start accidentally, oh, this is an x value, and they start using that for a y equation. It doesn't work that way. So when you set up this table here, just make sure you're really clear. Am I talking horizontal? Am I talking vertical? Anytime I need to put the two back together, I'm going to end up using Pythagoras. So let's have a look here. This initial velocity is 50 kilometers per hour. This is perfectly horizontal. This is perfectly sideways. So in the x, my horizontal velocity is 50. I do notice that, 50 is actually not my correct SI unit. So let's just divide by 3.6. Right, that's the magic number to convert exactly kilometer per hour to meter per second. Give or take a little bit of rounding here, I'm getting, let's say 14 meters per second. So 13.9, right? So 14. So I'm going 14. What we're going to do is we're going to assume there is no air resistance, right? When we're doing these problems here, let's make the problems as simple as we can. Because there is no air resistance, what is the acceleration in the x direction? Now, before you tell me acceleration is 9.8, remember acceleration for gravity is 9.8, but gravity pulls straight down. Whether it's me in free fall, whether it's me going to the side here, gravity just pulls downwards, but that's vertical. So if anything, if I wanted to label an acceleration under the y column, I can say negative 9.8, right? But that's in the y. What about the x? Well, the reason why the x velocity might change is because my wheels were actually rolling against the ground. If I step on the gas, my wheels spin a little bit faster, I can accelerate forwards. But the second that I'm actually off the ground, no matter how the wheels spin, there's no traction with any ground below. Pretty much what it's saying is, I left here with 50 kilometers per hour. A little bit later, I'm still 50. A little bit later, I'm still 50. Throughout the entire motion, I'm actually remaining 50. There is actually no horizontal acceleration. In the 3 styles of problems that we do over the next 2 days or so here, we will always have 0 horizontal acceleration. What horizontal acceleration could look like if this were like a rocket ship and you had boosters, and basically you can fire the boosters or fire the engines even if you're in the air, maybe you can accelerate, then there would be an A term. But for most of our questions here, we'll just be simple and we'll say no air resistance. So that's that. We have this distance of 100 meters. Where should I put that? Well, this 100 meters here is talking about an up and down. It's talking about the height of the cliff itself. Well, that's a y value. So I can actually say, well, the displacement in the y direction is going to be 100. And remember, using the sort of blindfold on, blindfold off, my blindfold is on when, again, this might explain why I'm driving off the cliff in the first place, but my blindfold is on when I'm at the top of the cliff, at the end of the motion. So I set initial to be here. I set my final to be down at the bottom. Even though the cliff itself is 100 meters, right, that's the magnitude of it, if I talk about displacement, I actually want to talk about I was higher and I'm now 100 meters lower, negative from where I started. I actually need to put a negative there, and I'm going to mean that as below. So again, just sort of reinforcing this idea, throughout this chapter, we seem to be really sloppy with positive and negatives because the negative just indicates to me direction. If I have a picture and I'm saying, oh yeah, I know it's negative, I might be able to just say in words, positive 100 meters below. What is the initial y velocity? Now this is a little more challenging because initially in x we said 50 kilometers per hour, right? I'm speeding off horizontally. But if we're now interested in the following part here, the instant that it leaves the ground, is it going up or down? I know an instant later, gravity would have started pulling downwards, but the second when I started the clock, I imagine the car has just left the cliff. It hasn't had a chance to actually fall down yet. So the initial velocity I'm actually going to put for the y direction, I'm actually going to put in that as 0. It's not going. So not going up or down immediately after leaving the cliff. Right? So when you're tempted to say, well, I thought initial velocity was 50. Yes, it was 50 horizontally, but in the vertically, in terms of the up and down direction here, gravity hasn't had a chance to actually start pulling it downwards yet. So we have separated our columns here. Those kinematic formulas, you can look back at your formula sheet here. They will work in either the x or the y. They can't take, oh, let's take an x velocity and let's use the y acceleration. It doesn't work like that. So usually what I do here, even if they didn't ask you part A, which they said find the total time, you try to find time, because once you find the time, the whole problem sort of falls apart. Sometimes you have more information in x, so you start on the x side. In this case here, I look like I have 3 numbers in y. Maybe I'm going to start off with the y. When I look at my kinematic formulas here, I'm going to actually, for these problems, I'm going to tend to prefer this one. D is equal to v naught t plus 1/2 at squared. If you look at the other two formulas that you have, the one with v final with time, v final with distance here, notice I don't know what the v final is just yet. And in fact, maybe in the next problem, if I ask you to calculate v final, maybe those other formulas would be helpful. But I want just a relationship between some of these variables, maybe even a relationship with time that doesn't involve v final right now. And remember, I'm using these equations just in y. So sometimes textbooks will actually say, what's your dy, what's your v naught y, what's your acceleration y. I'm going to find that you're not going to have that much trouble if you actually have this just separately in this column and you only use the values that I listed above. So let's try it here. I essentially am trying to fall negative 100. I'm going to be 100 below where I started. Initially, I wasn't going up or down, 0. Time is a scalar, that's why I don't need to say ty. So that's t there, plus 1/2. Acceleration is negative 9.8, and a t squared. So that's nice. I have one equation, one unknown. What's really nice about a meatball question, because the initial velocity here is 0, 0 kills off this term here with just t to the power 1. Because it kills off that term, I can just simply do a square root later on. So let's just work through some of the algebra here. Negative 100 is equal to negative 4.9 t squared. I'm going to bring the negative 4.9 over to the left-hand side. 100 divided by 4.9 gives me 20.4. And then I'm just going to take the square root. Whenever you take the square root, you get positive negative root here. Because time has to be positive, I'm going to opt for the positive answer. So what this is saying here is, from the start of the cliff, if you intend to fall 100 meters, and you know acceleration due to gravity is 9.8, it takes gravity some 4.5 seconds to actually drop you to the ground here. Now again, I don't know how fast it's going by the time it hits the bottom, but I know it is 4.5 seconds later. Again, you're going to backtrack and you're going to say, wait a second, this one here was actually a parabola. Is it okay that I adjusted the y? back to my thought experiment here, because both the parabola, even upon traveling through the more distance here, because they end up hitting at the same time, if I hit 4.5 seconds just dropping you here, dropping it even in this curve motion is also going to be 4.5. In the x direction, we have no idea that we're actually going to run into the ground. The x just keeps going 50, a little bit later 50, a little bit later 50, no horizontal acceleration. And now what if I say, okay, you need to stop at 4.5 because that's when I would have collided with the ground. That's when I have sort of, there's going to be some collision and the velocity is going to start changing. For the x direction then, to sort of answer part B here, so that's part A, let's find the time. Part B is interested in calculating the range. It's calculating the how far horizontally do I get, even though realistically your motion is very complicated. It's sort of this parabolic motion. If you tell me it took 4.5 seconds to actually hit the ground, this car here also has 4.5 seconds to go forwards. So initially it was going at 50 kilometers per hour. I converted it to 14 meters per second. A little bit later, still 14. A little bit later, still 14. A little bit later, still 14. So if you give me a time of 4.5 seconds, horizontally I can try using the same formula. D is equal to V naught T plus 1/2 AT squared. What's nice in our problems is because there is no horizontal acceleration, so make sure we know we're under the y column here. There is an acceleration due to gravity, but that's vertical. But because there's no horizontal acceleration, the a term is 0. That a term will kill off this entire half at squared term, and we're back to our basic motion equation. If we are going at 14 meters per second, and you now tell me I actually travel for that for 4.5 seconds, again, give or take a little bit of rounding, I get roughly 63 meters from the base of the cliff. And again, you might say, oh, I thought displacement was 100. It was 100 in the vertical. I have definitely dropped by 100 meters going downwards. But in terms of how far from the base of the cliff do I land, I've actually only gone 63 meters. So we've been able to separate a two-dimensional problem. We studied both parts separately, and we were able to find all this information. I'm going to give you another just practice of this meatball style question here. I'm going to play around with the variables that I'm asking for. So in this case here, let's say I have a car. So here's my car. I'm going to give it, again, an x velocity. The x velocity here is 10 meters per second. Right? So it's about 30, 40 kilometers per hour or so. Right? So again, we're a meatball. We just sort of drive off this cliff. I know I end up doing this parabolic shape. This time what I'm going to give you is actually the range. I'm going to tell you, well, when I watch this happen, you actually hit a point that's 50 meters away from you. My question in this one here, again, even if they don't ask you this, I would start off with this. Start off, find the time to reach the bottom. So how long are you in the air for? Sometimes you call it the flight time. B, this time the unknown is actually the height of the cliff. Last time it was, okay, we're 100 meter high cliff. I know in the vertical I have to drop by 100. This time I want you to calculate the height of the cliff. And then part C, I didn't ask you this earlier here, I want you to deduce or determine. They sometimes like changing this sort of keyword command term for you. Find, calculate, deduce. They just mean calculate it, determine it. That's the unknown that I'm looking for. So I want you to deduce the final velocity. And remember, when I say final velocity, it's the speed right before it's hitting. No matter how vertical this parabola looks like by the time it hits, because we are falling through 2 dimensions, I would expect my VF is also 2 dimensions. So the VF here is right before hitting. It is not after it's collided and lost energy, 0, right? It's not that. It's going to be the speed right before hitting. Speed right before impact. Right before it collides, right? So, again, this is a 2-dimensional problem here. Let's set up our 2 columns, right? So there's my x, and I'm going to have my y down here. Let's make a list of the variables that I know, just so that I can start thinking about what formulas I can do. Where would this 10 go, right? This time it's already in the correct units, which is nice, 10 meters per second, but this is me just driving straight horizontally. So my v initial in the x direction is going to be 10 meters per second. We knew there was no acceleration in the 0 direction. Again, we're assuming no air resistance. We actually know the range this time. We actually know horizontally from the base of the cliff, the displacement from when I start the clock to when I end, you're actually 50 meters in front of where you started, so that's going to be 50. In terms of the y, I don't know a lot. In terms of the y, I know the initial velocity. I know the instant I leave the cliff, Gravity hasn't had a chance to actually drag you up or downwards. The wheels are no longer in contact with the ground, so it can't speed you up from 10 meters per second. So V initial here is actually 0. We're not going up or down immediately when we leave the cliff, but I do know gravity, we're assuming we're on the Earth's surface, so negative 9.8 meters per second squared. Right? We don't know the displacement, right? I don't know the d there, and later on we're going to find the final velocity. So in the last question here, we actually knew more about the vertical, so that's why I started the formula there. This time I actually know a little bit more about the horizontal. I know the horizontal distance. And in fact, we just did this equation here. For horizontal, because the acceleration was 0, we just have a basic motion equation, d is equal to vt. If you tell me that you are traveling at 10 meters per second, and the distance that we actually travel is 50, how long a time would it have taken you to do that? In that case there, you just divide the 2 over. Oh, the time is just 5 seconds. Right? What we're going to see is the nice thing about finding time is actually a scalar. Time only has magnitude. So time doesn't care whether it was in the x column or the y column here, because it has no direction. Right? It has no heading or anything like that. Time is a variable that can jump between columns. So where earlier we were saying, well, x doesn't affect y, right? I can't put this 10 somehow in the y equations here because time doesn't have direction. If you had 5 seconds to go forwards, that's the same 5 seconds that gravity has to pull you downwards. So let's now take that time there. Let's do our typical formula here on the y side here. Because we do have an acceleration, I do need the full equation. So v naught t plus 1/2 at squared. Again, for a meatball style question, a little bit easier because initial velocity is actually 0 for the vertical. The time we just said was 5 plus 1/2. Acceleration is 9.8 with the 5 squared. Here we go. So 0 times 5 is 0. I'm going to type in the other part here, 0.5 times 9.8 times 5 squared. That becomes a negative 122.5. So my displacement there, 2 or 3 sig figs, so let's go negative 123 meters. Why is this answer here negative? Well, again, if you look back at the projectile here, we're saying, well, we started up here. If I call that my initial height, because this is negative, that negative just means I have fallen by 123 meters. So therefore, the height of the cliff, I can actually say the height is actually a positive 123. So this one here, I end up lower 123 meters. So therefore, the height of the cliff is just a positive 123 meters. That's when I actually collided with the ground. The last part here is interesting here. If I want to calculate the final velocity, like I mentioned, no matter how vertical this parabola, no matter how steep it looks like, because this is intrinsically a two-dimensional problem, I will still have a two-dimensional velocity at the end. So that's sort of going to be your diagonal, it's going to be your Pythagoras hypotenuse again. The x I actually already know. The x was 10. All throughout this motion, it's 10 and 10 and 10 and 10. That never changes because there was no x acceleration. So even in right before hitting, it's actually just going to go forwards at 10 meters per second. All I need to find here is I need to figure out here, if gravity had 5 seconds of time to speed you from not moving up or down, how much is the final velocity in the y direction? I've now created one last triangle here, and I can then do Pythagoras and put it back together to find that VF there. So let me just zoom in for that last part. This is part C of the question. I know eventually I've just sort of fallen down this parabola shape here. At the end, immediately before hitting, I will still be at some diagonal. The horizontal I knew. This is 10 meters per second. That number never changed. Let's find the Vy while I'm looking for the vertical again. So I'm down the vertical column. Now that I know a lot of information, I might go like V is equal to V naught plus AT. Remember, we had initially avoided these formulas because I didn't know VF or I didn't care about it. This time I actually want to find it. Initially, when I left the cliff, I'm not going up or down. The acceleration due to gravity is negative 9.8, and the time that I fall for is 5 seconds. So you do that there, I believe you get negative 49. The negative means downwards, so that means this speed here is actually 49. And now if you actually combine those back together, well, because my final velocity is actually at this diagonal, it's the hypotenuse of the triangle that I made here. We can then do our triangle work again. We can say, fine, our VF is equal to the root of 10 squared, the x velocity, and the y velocity. So let's type that in there, the root of 10 squared plus 49 squared. Make sure you use brackets. This gives me here 50 meters per second. It's slightly faster than the 49, you see that. And then again, because velocity is a vector, I also need to give you the angle. The angle is the inverse tan of opposite over adjacent. The opposite happens to be, for me, 49 divided by 10. Making sure you're in degree mode again here, divided by inverse tan 49 divided by 10. And this gives me here some 78 degrees. Again, when you're tempted to say, oh, I'm from the east direction, I'm aiming this much south, remember this is a side view problem, just like we did in the first question here. For a side view, we actually measure from the horizontal, and we're actually aiming 78 degrees lower than the horizontal. So you can actually use the terminology here, 78 degrees below the horizontal. Right? So try out some of your worksheet questions. Just try out separating the two components. Here's what I know about X, here's what I know about Y, and we'll pick it up from there tomorrow. Thanks, guys. Take care.